Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by the right triangle ABC. And in the second question, we'll find out the area of the blue right triangle that is inscribed by the quarter circle. We start with the first question. In the drawing, we have a right triangle ABC. Angle ABC equals to 90 degrees, side AB equals to 8 units. And we want to find out the radius of this circle that is inscribed by this triangle ABC. It is given us the question that the length of side BC and side AC are integers. Okay, and I want to find out the radius of this circle that is inscribed by the right triangle ABC. So first of all, we define side BC as A. And we will define the hypotenuse AC as B. In the next step, we will implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is AC and the square of the hypotenuse is AC squared. It is equal to the sum of the squares of the perpendiculars, that is to say, it is equal to AB squared plus BC squared. Repeat again, in the right triangle ABC, by PT is the equation for Pythagoras theorem, AC squared equals to AB squared plus BC squared. AC equals to B according to our definition, so AC squared is B squared. That is equal to AB squared. AB is 8, so AB squared is 8 squared, that is 64, plus BC squared. BC equals to A according to our definition, so BC squared is A squared. In conclusion, we found out that according to the equation number 1, B squared equals to 64 plus A squared. Here we will subtract A squared from this equation number 1, and we get that B squared minus A squared equals to 64. We have the algebraic identity that B squared minus A squared equals to B plus A times B minus A. So we substitute b squared minus a squared by b plus a times b minus a. And according to equation number 1, it is equal to 64. So it is given us the question that AC and BC are integers. That is to say, BC equals to A and AC equals to B. So you can write down that A and B are integers. And we also know that A and B are the lengths of the sides of the right triangle ABC. Therefore, A and B, we know that they are lengths. So as lengths, there must be positive numbers, so they are positive. So from 1 and 2, we derive that A and B are positive integers. Okay, so we know that A and B are positive integers. And because of the fact that A and B are positive integers, it is obvious that A plus B must be greater than, or B plus A must be greater than B minus A. Because when you add two positive integers to each other, the sum must be greater than the situation, than the case that when you subtract them by each other. And we know that B is integer and A is integer, therefore B plus A, B is a positive integer and A is a positive integer, therefore B plus A is also a positive integer. And B is the hypotenuse, and the hypotenuse is greater than the perpendicular, so B is greater than A. If we subtract A from this inequality, we get that B minus A is greater than 0, that is to say B minus A is a positive. Therefore, we can write down that B minus A is a positive integer. Why? Because if B is a positive integer and A is a positive integer, then B minus A also must be a positive integer, because we know from the beginning that B minus A is a positive, therefore it must be a positive integer. Okay. So, according to question number 1, if you multiply the number, the positive integer b plus a by the positive integer b minus a, we get the result of 64. So actually there are not a lot of possibilities that the multiplication of two positive integers will give us the result of 64. So we will write down all the possibilities that the multiplication of two positive integers will give us 64. Okay. So the first option is that the positive integer b plus a is 1 and the positive integer b minus a is 64, and 1 times 64 is 64. The second possibility is that the positive integer b plus a is 2 and the positive integer b minus a is 32, and 2 times 32 is 64. The first possibility is that b plus a equals to 4 and b minus a equals to 16, and 4 times 16 is 64. The fourth possibility is that b plus a equals to 8 and b minus a equals also to 8, and then 8 times 8 is 64. Then we have the next possibility that b plus a is 16 and b minus a is 4, and 16 times 4 is 32. Then we have the possibility that b plus a is 32, b minus a is 2, and 32 times 2 is 64. And the last possibility is that b plus a is 64 times, and b minus a is 1, and 64 times 1 is also 64. So we have here 7 possibilities for the solution of the problem, and because of the fact that we know that b plus a is greater than b minus a, it means that the first column must be greater than the second column. So we must cancel, delete all the possibilities that are not obeyed to the following rule, that the first column must be greater than the second column, because b plus a must be greater than b minus a. So we check each of the possibilities to check if the first column is greater than the second column. And if it is not greater, then we will cancel this possibility. It is not a good possibility, because b plus a must be greater than b minus a. So if 1 is not greater than 64, so this option will be cancelled. 2 is not greater than 32, therefore this option will get cancelled. 4 is not greater than 16, so we'll cancel this option. 8 is not greater than 8, we'll cancel this solution. 16 is greater than 4, therefore this option is a good option. This solution is a good solution. 32 is also greater than 2, it is a good option. And 64, it is also greater than 1, that is to say, it is also a good option. So, in conclusion, we have only just 3 possibilities that are left. In the next step, we'll add the two numbers together in order to find out the result. That is to say, we'll add b plus a to b minus a, and we'll see what is the result. Here, b plus b is 2b, and a minus a is 0. b is a positive integer, therefore 2 times b is an even number. That is to say, when we add the two numbers together, the result must be an even number. Otherwise, we'll cancel this possibility, because the result must be an even number. If it is an odd number, it is not a good option, because b plus a plus b minus a is an even number. So we'll check here in which case the sum of the two numbers together, when we add the two numbers together, we'll get an even number. So here 16 plus 4 is 20. 20 is an even number, therefore this is a good possibility. 32 plus 2 is 34. 34 is an even number, therefore it is also a good possibility. But 64 plus 1 is 65, that is an odd number. It is not an even number, so this solution is not a good solution. So we left only two solutions that are possible for the question, that b plus a is 16 and b minus a is 4. And the second solution is that b plus a is 32 and b minus a is 2. Okay, so write down the two solutions to the question. So according to the first solution to the question, b plus a is 16, and b minus a is 4. And the second solution to the question is that b plus a is 32, and b minus a is 2. So we'll focus on the first solution. Here we will add the two equations together. B plus b is 2b. And 16 plus 4 is 20. So we got the equation that 2b equals to 20. We will divide this equation by 2, and we get that b equals to 20 over 2 is 10. So we found out that the hypotenuse B equals to 10 units. In the next step we'll find out the value of A. According to this equation, B plus A equals to 16. We subtract B from this equation and we get that A equals to 16 minus B. We have already found out that B equals to 10 units, so we substitute B by 10 and we get that A equals to 16 minus B is 10 and 16 minus 10 is 6. So in conclusion, we found out that according to the first solution, the value of A, that is the perpendicular, it is equal to 6 units, and the value of A is 6 units, and the value of B, the hypotenuse, is equal to 10 units. This is the first solution. The second solution is 32 and 2. We add the two equations together to each other and we get that B plus B is 2B, A minus A is 0, so here in the other side of the equation we have 32 plus 2 is 34. So in conclusion we found out that 2B equals to 34. We divide this equation by 2 and we get that B equals to 34 over 2 is 17. So the hypotenuse equals to 17. The next step we find out the value of A. According to this equation, B plus A equals to 32. Here we subtract B from this equation and we get that A equals to 32 minus B. So A equals to 32, and we already found out that B equals to 17, so we substitute B by 17 and we get that A equals to 32 minus 17, that is 15. So according to the second solution to the question, we found out that A equals to 15 and the hypotenuse B equals to 17. So I will draw, in the next step I will draw the two right triangles that are the solutions to the question. The first right triangle, triangle ABC, the right triangle, triangle ABC. First of all, it is given us the question that AB equals to 8 units. We have right now found out that BC equals to 6 units and the hypotenuse AC equals to 10 units. Actually, in this specific right triangle, triangle ABC, we have a circle that is inscribed by this triangle and we are looking for the radius of this circle. Find out the length of the radius of this circle that is inscribed by the right triangle, triangle ABC. So this is the circle that is inscribed by the right triangle, triangle ABC, and we want to find out the radius of this circle. So we define the radius of capital R, and we are looking for the radius of this circle that is equal to capital R. This is the first possibility for the solution, but we also have the second right triangle, triangle ABC. The second right triangle, triangle ABC, we know that AB equals to 8 units, and found out that BC equals to 15 units, and the hypotenuse AC equals to 17 units. Inside this right triangle, triangle ABC, we have a circle that is described by the triangle. This is the circle that is described by triangle ABC, the right triangle ABC. When we're actually looking for the radius of this circle that is described by triangle ABC. So here we're looking for the radius of this circle that is described by triangle ABC that is equal to capital R. Okay? So those are the two possibilities, the two right triangles that are solving our problem, our question. In the next step, we will find out the radii of the two right triangles, triangle ABC, and we actually take right triangle, triangle ABC that could be any triangle, and we find out the radius of this circle that is described by the right triangle, triangle ABC that could be any triangle, that could be any right triangle. Okay, so first of all we define the length of side AB as A. That is to say, side AB of the right triangle ABC equals to A according to our definition. We define the length of side BC of the right triangle, triangle ABC as B. When we define the hypotenuse AC of the right triangle, triangle ABC is C. And we want to find out the radius of this circle, but that is described by this triangle, triangle ABC. Okay, so we'll define the center of this circle as O. We'll define the point of tendency of tangent BC with this circle as M. We'll define the point of tendency of tangent AB with this circle as N. In the next step, we join points N and O together by a straight line. Here, point O is the center of the circle. Point N is the point of the circle itself. So this is exactly the definition of a radius. So NO is the radius of this circle that is equal to capital R according to our definition. Then we have here rule number 1 that says that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here the radius ON, it is drawn to the point of tendency, this is to say it is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO according to rule number 1, it means that this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to rule number 1. Likewise, we have here the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also will be equal to 90 degrees according to rule number 1. So actually in quadrilateral NOBM, we have 3 right angles that each of them is equal to 90 degrees, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle NOM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral NOBM to 360 degrees. This angle must be equal to 90 degrees, because 270 degrees plus 90 degrees is 360 degrees. So further, that inside quadrilateral NOBM, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. So NO equals to BM from one side, but we also know that NO equals to R from the other side. Therefore, BM that is equal to NO must be also equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that NB equals to OM. NB equals to OM from one side, but from the other side, we have already found out that OM equals to R, and NB also equals to OM. Therefore, NB must be also equal to R. So we found out that quadrilateral NOBM, it is not a rectangle but a square, because all of its sides are equal to each other. In the next step, we'll find out the length of line segment AN. From the drawing, it is very easy to see that AN equals to AB minus LB. Again, AB minus LB equals to AN. That is to say, AN equals to AB, that is A, minus LB, that is R. So in conclusion, we found out that AN equals to A minus R. And here we find out the length of line segment MC. From the drawing, it is very easy to see that MC equals to BC minus BM. So MC equals to BC, that is B, minus BM, that is R. So in conclusion, we found out that MC equals to B minus R. Okay, so in conclusion, we found out that MC equals to B minus R and NA equals to A minus R. In the next step, I will present to you rule number 2. According to rule number 2, the lengths of 2 tangents from a common external point to a circle are equal. I repeat again, the lengths of 2 tangents from a common external point to a circle are equal. So if we focus on the common external point, point A, we have 2 tangents to this circle. Tangent AN, here. The second tangent, we define the point of tangency of tangent AC with this circle as L. So we have, from point A, we have 2 tangents to this circle, tangent AN and tangent AL. And according to rule number 2, they must be equal to each other. That is to say, AN equals to AL from one side, but from the other side, we have already found out that AN equals to A minus R. Therefore, AN must be also equal to A minus R. In the next step, we focus on the common external point, point C. From the common external point, point C, we have 2 tangents to this circle, tangent CM and tangent CL. According to rule number 2, they are equal to each other. That is to say, CM equals to CL. But we have already found out that CM equals to V minus R. And CL also equals to CM. Therefore, CL must be also equal to B minus R. Okay, so in conclusion, we found out that AL equals to A minus R and LC or CL equals to B minus R. So what is the length of the hypotenuse AC? From the drawing, it is very easy to see that the length of the hypotenuse AC, it is equal to AC equals to AL plus LC. AL plus LC, I will put again. AC equals to AL plus LC. Okay. According to our definition, AC equals to C. So we substitute AC by C. So C equals to AL. AL equals to A minus R. We substitute AL by A minus R. Plus LC. LC equals to B minus R. So we substitute LC by B minus R. So in conclusion, we found out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B minus R plus minus R is minus 2R. Here we add 2R to this equation and we get that C equals to A 2R plus C equals to A plus B. Here we subtract C from this equation and we get that 2R equals to A plus B minus C. We divide this equation by 2 and we get that R equals to A plus B minus C over 2. So actually we found out a general formula by which we can, and according to this general formula, by using this general formula we can find out the radius of any circle that is described by a right triangle. That is to say, we can use this formula in order to find out the radii of those two right triangles. I'll copy here this new formula. R equals to A plus B, that is the sum of the perpendiculars, minus C is the hypotenuse, over 2. So we'll find out the radius of the first circle that is described by this specific triangle, triangle ABC. So the radius will be equal to A plus B is the sum of the perpendiculars. It is 8 plus 10, 8 plus 6. The sum of the perpendiculars is 8 plus 6. Minus C is the hypotenuse, minus 10 over 2. So 8 plus 6 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is described by this specific right triangle, triangle ABC equals to 2 units, equals to 2. This is the first solution to the question, and also another solution. Here we find out the second option. According to this formula, that R equals to A plus B is the sum of its perpendiculars. It is 8 plus 15 minus C is 17 over 2. So here 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So the second solution to the question is the radius of this specific circle that is described by this specific right triangle, triangle ABC, equals to 3 units. So actually found out two solutions to the question. here the radius of this circle that is described by the radius of this specific circle that is described by this specific right triangle, triangle ABC, equals to either 2 units or 3 units. So here the radius of the circle that is described by the right triangle, triangle ABC, equals to either 2 units or 3 units. And that is the answer to the question. In the next step, I will present to you the second question, and we'll solve the second question in 2 different methods. Okay. In the drawing, we have a quarter circle, and we know that side OB equals to 2 units. We know that AD equals to DO. Inside this quarter circle, we have this light blue triangle, angle BC, D equals to 90 degrees, and we want to find out the area of this light blue triangle BCD. So we'll start with the first method. AOB is a quarter circle, therefore this angle, it is a right angle, it is equal to 90 degrees. It is true in any quarter circle. And point O is the center of the quarter circle. Okay? And the radius of this quarter circle equals to OB, and it also equals to OA. And we know that the radius OB equals to 2 units, therefore the radius OA also equals to 2 units. So here we can write down that AO equals to OB. It is the radius of the quarter circle that, according to what is given us, it is equal to 2 units. So AO equals to OB equals to the radius of the quarter circle that is equal to 2 units. But according, for the drawing, it's very easy to see that AO equals to AD plus DO. AD plus DO equals to AO. This is the radius of this circle that is it is the radius of the quarter circle that is equal to 2 units. But because of the fact that AD equals to DO, it means that if AD equals to X, then DO also equals to X. So AD plus DO equals to X plus X. X plus X is equal to 2X, equals to 2X, and here from this long equation we derive that X plus X, that is 2X, equals to 2. Here we divide this equation by 2 and we get that X equals to 1 unit. So here AD that is equal to X equals to 1 unit, and DO that is also equals to X equals also to 1 unit. In the next step we will complete the quarter circle to a circle. So I completed the quarter circle to a circle. In the next step we will extend the radius BO by a straight line until it touches the circle. We define the touching point of the extended BO in the circle as point P. Point P and point O is the center of the circle. Point P is the point of the circle itself. This is exactly the definition of a radius. That is to say, PO or OP is the radius of this circle that is equal to 2 units according to what is given as the question, because of the fact that the radius of this circle is also the radius of the quarter circle that is equal to 2 units. Okay, so in the next step, here we extended the radius BO by a straight line. BO as a radius, it is a straight line, and when you extend a straight line by a straight line, the result is a straight line. So here BP is the diameter of the circle because of the fact that it passes from point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. So you can write down that BP is the diameter of the circle. And as I already mentioned, also BP is the diameter of a circle is absolutely a straight line, and we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line BP at point O, the sum of the angles here must be equal to 180 degrees. This angle equals to 90 degrees, so this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of the straight line BP at point O to 180 degrees. This angle must be also equal to 90 degrees. And point O is the center. Okay, in the next step we will extend side CD by a straight line until it touches the circle. So we don't know where the extended line segment CD will touch the circle. So suppose that the extended side CD will touch the circle at point in this point X. Okay, suppose that when you extended side CD by straight line, it will touch the circle at point X. Okay, so we actually created here peripheral angle BCX. We have peripheral angle BCX. BCX is a peripheral angle because it touches the circle at point B and point X, and the vertex is at point C. So BCX is a peripheral angle and we also know that this peripheral angle BCX equals to 90 degrees. It is given as the question. So peripheral angle BCX equals to 90 degrees. But according to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. We get here a contradiction because we have here peripheral angle BCX that is equal to 90 degrees, and it is not rest on the diameter of the circle that is BP. So there is a contradiction. We have peripheral angle that is equal to 90 degrees, and it is not resting on the diameter of the circle that is PB. So in order to avoid the contradiction, point X must merge with point P. Okay, point X must merge with point P in order to avoid the contradiction, and then we'll get that indeed peripheral angle BCP rests on the diameter that is BP, that is PB. So here, if point X merge with point P, we'll get here peripheral angle BCP that is resting on the diameter of the circle. Okay, actually we arrive to the conclusion that peripheral angle BCX that is equal to 90 degrees, it is also equal to peripheral angle BCP, that is to say point X merge with point P. Okay, in this way we get that peripheral angle BCP equals to 90 degrees, and indeed this peripheral angle that is a right angle that is equal to 90 degrees, it indeed rests on PB, that is the diameter of the circle. Okay, so in the next step we'll find out the hypotenuse PD of the right triangle, triangle POD. In the right triangle POD, according to the Pythagoras theorem, by PT is abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say PD square equals to PO square plus OD square. I repeat again, in the right triangle, triangle POD, PD square equals to PO square plus OD square. So PD square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus PO square. PO is 2, so PO square is 2 square, that is 4. So in conclusion, we found out that PD square equals to 4 plus 1, that is 5. We take out all of this equation and we get that the hypotenuse PD equals to the square root of 5 units. Okay, the hypotenuse PD equals to the square root of 5 units. You can write here that PD equals to the square root of 5 units. We repeat on the same process on the right triangle, triangle DOB. On the right triangle, triangle DOB, by PT we get the DB square equals to DO square plus OB square. Repeat again, in the right triangle, triangle DOB, according to the Pythagoras theorem, dB square equals to d whole square plus OB square. So dB square equals to d whole square, that is 1 square is 1, plus OB square. OB is 2, so OB square is 2 squared, that is 4. So, in conclusion, we found out that dB square equals to 1 plus 4, that is 5. Here we take out all of this equation and we get that dB equals to the square root of 5 units. So we can write down here that dB equals to square root of 5 units. In the next step, we'll extend the radius AO by a straight line until it touches the circle, and we'll define the touching point of the extended radius AO in the circle as point Z. Here, point O is the center of the circle. Okay, point Z is a point on the circle itself. This is a graphic designation of a radius. That is to say, OZ is the radius of this circle, that is equal to 2 units. In the next step, we will implement rule number 1 in our drawing. Rule number 1 deals with 2 chords that intersect with each other inside the circle. We have I've already mentioned it a couple of times in the previous lectures. So actually, if we have a circle and inside the circle we have 2 chords. In chord, this is chord AB. That intersects with chord CD. This is called CD at point O. Chord AB intersects with chord CD at point O. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Okay, again, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing, because in our drawing we have chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. Write it down. Chord AZ intersects with chord CP, and the intersection point is at point D. Okay, therefore according to rule number 1, we get that AD times DZ will be equal to CD times DP. Repeat again. AD times DZ equals to CD times DP according to rule number 1. So AD equals to 1. DZ equals to 1 plus 2, that is 3. And it is equal to CD times DP. DP equals to square root of 5 units. And CD is the missing 9 segments. So in conclusion, we found out that 3 equals to square root of 5 times CD. We divide this equation by square root of 5 and we get that CD equals to 3 over square root of 5 units. Here CD equals to 3 over square root of 5 units. You can write here that CD equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle CDB. According to the Pythagoras theorem on the right blue triangle, triangle CDB, the square of the hypotenuse equals to the sum of the square of the perpendicular, that is to say dB square equals to DC square plus CB square. Repeat again. In the right triangle CDB, according to the Pythagoras theorem, dB square equals to DC square plus CB square. So dB equals to the square root of 5, therefore dB square is square root of 5 squared, that is 5, and it is equal to DC square. DC is 3 over square root of 5, so DC square is 9 over 5, plus CB square is the missing 1 segment. So I found out that 5 equals to 9/5 plus CB square. We subtract 9/5 from this equation and we get that 5 minus 9/5 equals to CB square. Here we'll multiply 5 by 5 and then we divide it by 5. In order to have a common factor with this expression, so 5 times 5 is 25 minus 9 over 5 equals to CB square. (25 minus 9 is 16 over 5 equals to CB square). We take out all of this equation and we get that CB equals to the square root of 16, that is 4 over the square root of 5. So I found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of the blue white triangle, triangle CDB. It will be equal to the base of the triangle, that is CD, times the height of the base, that is CB, over 2. So the area of the blue triangle, blue right triangle, triangle CDB will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. I repeat again, the area of the blue right triangle, triangle CDB equals to the base of the triangle, that is CD, times the height of the base, that is CB, over 2. So DC equals to 4 over square root of 5 times CB is 4 times square root of 5, all divided by 2. Okay, so here in the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6. So in the numerator we have 6. In the denominator what is left is only 5. So in conclusion we found out that the area of the blue right triangle CDB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finished with the first method. In the next step I present to you how to find out the area of this blue right triangle DCB according to the second method. So, you know, according to the first method, that this angle equals to 90 degrees. We also found out that AD equals to 1 unit, DO equals to 1 unit in the first method. In the next step, we complete the quarter circle to a semicircle. Actually, we complete the quarter circle to a semicircle. So here we have a semicircle, not a circle. So this is the semicircle. In the next step, we'll extend the radius BO by a straight line until it touches the semicircle. In this point, point P is the touching point of the extended radius BO and the semicircle. Okay. O is the center of the semicircle, P is the point of the semicircle itself, therefore PO is the radius of the semicircle, that is equal to 2 units according to what is given as the question. Okay. Here we will extend side CD by a straight line until it touches the circle, until it touches the semicircle. And according to the first method, we've already proved that when we extend side CD by a straight line, it must touch the circle at point P. At point P, only at point P. Okay? We've already found out that angle AOP equals to 90 degrees. We've already found out that the hypotenuse PD in the right triangle POD equals to square root of 5 units. And we've already found out that the hypotenuse DB in the right triangle DOB also equals to square root of 5 units. We'll define angle DPO as theta. In the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle PDO to 180 degrees, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. And we'll focus on the right triangle BCP. In the right triangle BCP, this angle equals to theta, this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees minus theta. Exactly for the same reason that this angle also equals to 90 degrees minus theta. Okay, in order to complete the sum of the angles, so 180 degrees, this angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the right triangle PDO is similar to the right big triangle, triangle PCB. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle POD equals to angle PCB, and they are both equal to 90 degrees. I repeat again, angle POD equals to angle PCB, they are both equal to 90 degrees, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle PDO equals to angle PBC, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. Here I repeat again, angle PDO equals to angle PBC, and they are both equal to 90 degrees minus theta. And finally, this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So angle DPO equals to angle CPB, that is equal to theta. Repeat again, angle DPO equals to angle CPB, that is equal to theta. That is to say, it is a common angle that belongs to both triangles. So actually we proved that all the angles of triangle PDO can go into all the angles of triangle BCB. Therefore, a triangle PDO is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is also equals to PO over PC. Repeat again, from the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB equals to PO over PC. So here, PD is equal to 5 units over PB. PB equals to 2 plus 2, that is 4. That is equal to DO. DO equals to 1. CB is a missing line segment, so we leave it as it is. And it is equal to PO. PO equals to 2 units over PC. PC equals to square root of 5 units plus DC. So in conclusion, we found out the square root of 5 over 4 equals to 1 over CV equals to 2 over square root of 5 plus DC. We will derive from this long equation the first equation, that square root of 5 over 4 equals to 1 over CB. Here we will cross multiply this equation, equation number 1, and we will get that according to equation number 1, square root of 5 times CB equals to 4. Here we divide this equation, equation number 1, by square root of 5, and we get that according to equation number 1, CB equals to 4 over square root of 5 units. So we can write down in the drawing that CB equals to 4 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle CDB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the square of the perpendiculars. That is to say, dB square equals to dC square plus CB square. In the right triangle, triangle DCB, according to the Pythagoras theorem, dB square equals to dC square plus CB square. So dB is square root of 5, so dB square is square root of 5 squared, that is 5. That is equal to dC square. This is the missing line segment, so we leave it as it is, plus CB square. CB is 4 over square root of 5, so CB square is 16 over 5. So in conclusion, we found out that 5 equals to dC square plus 16 over 5. We subtract 16 over 5 from this equation, and we get that only to this equation, 5 minus 16 over 5 equals to dC square. Here we will multiply this equation by 5, and then we divide it by 5 in order to overcome the factor of this expression. So 5 times 5 is 25, minus 16 over 5 equals to dC square. Here 25 minus 16 is 9, so we have 9 over 5, that is equal to dC square. Here we take out of this equation, and we get that dC, the missing line segment dC, equals to the square root of 9, that is 3, over square root of 5. So in conclusion, we found out that dC equals to 3 over square root of 5. dC equals to 3 over square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. I repeat again, the area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So here, DC equals to 3 over square root of 5 units. CB equals to 4 over square root of 5 units. All divided by 2. So here, 3 times 4 is 12. square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6, so in the numerator we have 6. And then the numerator what is left is only 5. So we found out that the area of the right blue triangle DCB equals to either 6 over 5 square units, so in terms of numbers it is equal to 1.2 square units. We finish with the second method. In the next step I will summarize the lecture. We'll start with the first question. So in the drawing, we have the right triangle ABC. Side AB equals to 8 units. We also know that side BC and side AC are integers. Angle ABC equals to 90 degrees. Inside this right triangle ABC, we have this circle that is inscribed by triangle. And we want to find out the radius of this circle that is inscribed by triangle ABC. So first of all, we define side BC as A and side AC, the hypotenuse AC as B. And then we implemented the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC squared equals to AB squared plus BC squared. AC is B, so AC squared is B squared. AB is 8, so AB squared is 8 squared, that is 64, plus BC squared. BC is A, so BC squared is A squared. So in conclusion, we found out that according to equation number 1, B squared equals to 64 plus A squared. We subtracted A squared from this equation number 1, and we found out that B squared minus A squared equals to 64. Then we used the algebraic identity that B squared minus A squared equals to B plus A times A B minus A. So we substituted B squared by B plus A by B minus A. And according to equation number 1, it is equal to 64. So we know that A and B, AC equals to B and BC equals to A, and AC and BC are integers, therefore A and B also will be integers. And we know that A and B are the lengths of the sides of the right triangle. Therefore, there must be a positive number. So from 1 and 2, we get that A and B are positive integers. Okay? But if we have positive integers, then B is a positive integer, A is a positive integer. Therefore, B plus A must be greater than B minus A, because when you add two positive integers to each other, it must be greater than the case that when you subtract them from each other. So B plus A must be greater than B minus A. B is integer, A is integer, therefore B plus A must be also B is a positive integer, A is a positive integer, therefore B plus A must be also a positive integer. And we know that B is the hypotenuse, it is always greater than the perpendicular that is A. So B greater than A. We subtracted A from this inequality, and we got that B minus A is greater than 0, that is to say B minus A is a positive number. Because of the fact that B is a positive integer and A is a positive integer, then B minus A, if it is a positive, it must be also a positive integer. So we found out that both those two numbers are positive integers. Actually, according to equation number 1, when we multiply two positive integers together, the result is 64. And there are not a lot of possibilities that the multiplication of two positive integers will give us 64. So we wrote down all the possibilities. The first possibility is 1 and 64, the second is 2 and 32, the third is 4 and 16. The fourth is 8 and 8, the fifth is 16 and 4, the sixth is 32 and 2, and the last one is 64 and 1. Those are all the possibilities for two integers that when you two positive integers that when you multiply by each other, that when you multiply them by each other, the result must be 64. So we have seven possibilities, but because of the fact that b plus a is greater than b minus a, it means that the first column, here b plus a, that is the first column, must be greater than the second column. So all the possibilities that will not give us that the first column is greater than the second column, it is not valid possibilities. We will cancel these possibilities because the first column, that is b plus a, must be greater than the second column, that is b minus a. So here 1 is not greater than 64, we will cancel the solution. 2 is not greater than 32, we will cancel the solution. 4 is not greater than 16, we will cancel the solution. 8 is not greater than 8, so we will cancel the solution. So we left only if 16 is greater than 4, it is a good solution. 32 is greater than 2, this is a good solution. And 64 is greater than 1, that is also a good solution. So we have here 3 possibilities to the answer. But in the next step we will add the two numbers together, the two positive integers together, in order to find out the value of the result. So we added the two numbers together, b plus a plus b minus a. So b plus b is 2b and a minus a is 0. So in conclusion, so b plus b is 2b. So the result of the adding the two numbers together is 2b, that is an even number. That is to say, if we add the two numbers together, the result must be an even number. That is to say, if we will not get an even number, we will cancel this solution because the result must be an even number. So we'll check which of the options will give us an even number. Here 16 plus 4 is 20, it is an even number, 20 is an even number, so it is a good solution. 32 plus 2 is 34, that is also an even number, it is also a good solution. And finally 64 plus 1, it is an odd number, it is not an even number, therefore we'll cancel this solution. And we left only with two possible solutions to the question, 16 and 4 and 32 and 2. Okay, so here, according to the first solution, b plus a is 16 and b minus a is 4. And according to the second solution, b plus a is 32 and b minus a is 2. So we added we focused on the first solution and we add the first equation to the second equation, and we found out that b plus b is 2b, a plus minus a is 0, that is a minus a is 0. So in this side of the equation we have 2b, and 16 plus 4 is 20, so we found out that 2b equals to 20, we divided this equation by 2 and found out that the hypotenuse b equals to 10 units, and found out the value of a. According to this equation, b plus a equals to 16, we subtracted b from this equation and found out that a equals to 16 minus b. So a equals to 16 minus b, that is 10, so 16 minus 10 is 6. So in conclusion, we found out that according to the first solution, the perpendicular a equals to 6 units and the hypotenuse b equals to 10 units. According to the second solution, here we added the two equations together, b plus b is 2b and a minus a is 0. So in this side of the equation we have 2b, and the other side of the equation we have 32 plus 2, that is 34. So according to this equation, 2b equals to 34. We divided this equation by 2 and found out that b equals to 34 over 2 is 17. Okay, so the hypotenuse b equals to 17, and we have this equation that b plus a equals to 32. We subtracted b from this equation and found out that a equals to 32 minus b. and B is 17, so A equals to 32 minus 17, that is 15. So in conclusion, according to the second solution, the perpendicular A equals to 15 and the hypotenuse B equals to 17. So I drew the two solutions here. According to the first solution, AB is 8 units, BC is 6 units, and the hypotenuse AC is 10 units. Inside this right triangle, we have this circle that is inscribed by the right triangle. I want to find out the radius of this circle. Then I draw the second right triangle that we get from the solution. AB is 8 units, BC is 15 units, and the hypotenuse AC equals to 17 units. And inside this right triangle, triangle ABC, we have this circle that is inscribed by the right triangle ABC, and we want to find out the radius of this circle. In order to find out the radius of the radii of the two circles, we actually draw a right triangle ABC. Here, the right triangle ABC could be any triangle. This is the right triangle ABC that could be any triangle. Inside this right triangle ABC, we have this circle that is inscribed by the right triangle ABC, and we'll find out the general formula for the radius of this circle, and we'll implement this formula in our two triangles. Why can we implement the new formula in our two right triangles? Because of the fact that this triangle ABC, could be any triangle, especially out of those two triangles. Therefore, we can implement the new formula in our two triangles, triangle ABC. So, because of the fact that triangle ABC could be any triangle, we'll define AB as A, we'll define BC as B, and we'll define the hypotenuse AC as C. Okay? And then we'll define the point of tendency of tangent AB with the circle as N, we'll define the point of tendency of tangent BC with the circle as M, and we'll define the point of tendency of tangent AC with the circle as L. Then we define the center of the circle as point O, and we join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of this circle. So here we have rule number 1, that the tangent to a circle is perpendicular to the radius known to its point of tendency. We have the radius ON that is known to the point of tendency, that is to say it is known to point N, that is the point of tendency of tangent AB with the circle, and whenever we have a radius that is known to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if tangent AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees, according to rule number 1. Likewise, we have the radius OM that is known to the point of tendency. Therefore, tangent BC will be perpendicular to the radius MO, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. In quadrilateral NOBM, we have 1, 2 free right angles. The sum of free right angles is 270 degrees, plus the fourth angle, that is angle NOM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. That is to say, the fourth angle must be equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral NOBM, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. This is to say NO equals to BM. NO equals to BM for one side, but we have already found out that NO equals to R, therefore BM also must be equal to R. Likewise, according to the same rule, the opposite sides of rectangle are equal to each other, we get that NB equals to OM for one side, but from the other side we have already found out that OM equals to R. Therefore, NB that is equal to OM must be also equal to R. So We found out that quadrilateral NOBM is a square, is not a rectangle, because all of its sides are equal to each other. Then we found out the length of line segment AN equals to AB minus NB. AB minus NB, that is to say, AN equals to AB, this is A, minus NB, this is R. So in conclusion, A equals to A minus R, AN equals to A minus R. And we found out the length of line segment MC equals to BC minus BM. That is to say, MC equals to BC, that is B, minus BM, that is R. In conclusion, MC equals to B minus R. Okay, MC equals to B minus R, and AN equals to A minus R. Then I presented to you rule number 2, that the tangent to a circle is perpendicular to the radius known to its point of tendency. So if you focus on the common standpoint point A, from the common standpoint point A, we have two tangents to the circle, tangent AN and tangent AN. And according to rule number 2, they are equal to each other. That is to say, AN equals to AN. But we have already found out that the AN equals to A minus R, therefore AN must be also equal to A minus R. Likewise, we focus on the common standpoint point C. From the common standpoint point C, we have two tangents to the second, tangent CM and tangent CL. And according to rule number 2, they are equal to each other. This is to say, CM equals to CL for one side, but from the other side, we have already found out that CM equals to B minus R, and CM also equals to CL. Therefore, CL must be also equal to B minus R. So in conclusion, we found out that AL equals to A minus R and LC equals to B minus R. Then we found out the length of the hypotenuse AC equals to AL plus LC. Here AC equals to AL plus LC. According to our definition, AC equals to A, AL equals to A minus R, AL equals to A minus R, and LC equals to B minus R. So in conclusion, C equals to A minus R plus B minus R. That is to say, C equals to A plus B, minus R plus minus R is minus 2R. We added 2R to this equation and found out that 2R plus C equals to A plus B. We subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that the radius that we are looking for, the radius of this circle that is inscribed by any right angle, it is equal to A plus B, that is the sum of the perpendiculars, minus C, that is the sum, that is the hypotenuse, over 2. Okay, so in any right triangle, this is a valid formula to find out the radius of any circle that is described by any right triangle. Especially you can implement the new formula in our two right triangles that we have here. This is the new formula. According to this new formula, R equals to A plus B, that is the sum of its perpendiculars. Here it is 8 plus 6, minus the hypotenuse AC, that is 10 over 2. 8 plus 6 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of the circle here is 2 units. Then, according to the second solution, we have this right triangle. Here R equals to the sum of the perpendiculars, that is 8 plus 15, minus the hypotenuse, that is 17 over 2. 8 plus 15 is 23, minus 17, 23 minus 17 is 6, and 6 over 2 is 3. So in conclusion, we found out that we have two solutions to the question, that the radius of this circle, that is described by the right triangle, triangle ABC, would be equal to either 2 units or 3 units. And that is the answer to the question. The next I will present to you the second question. So in the drawing, we have a quarter circle side OB of the quarter circle equals to 2 units. AD equals to DO. Inside this quarter circle we have this right blue triangle, triangle DCB, and we want to find out the area of this right blue triangle, triangle DCB. So first of all, because of the fact that AOB is a quarter circle, this circle equals to 90 degrees. The center of this quarter circle is point O, and the radius of the quarter circle is OB is 2 units. It is also equals to AO. So here AO equals to AD plus DO, and AO equals to also OB. Both AO and OB are the radii of the quarter circle. Now the radius of the quarter circle that is equal to 2 units according to what is given as the question. We defined AD as x, therefore DO must be also equal to x. So AD plus DO is x plus x, that is 2x, and 2x equals to 2 according to this equation. We divided this equation by 2 and we found out that x equals to 1 unit. Here AD that is equal to x is 1 unit, and DO this is also equal to x, it is also 1 unit. Okay, then we completed the quarter circle to a circle, and then we extended the radius BO by a straight line until it touches the circle at point P. P is O is the center of the circle, P is the point of the circle itself, therefore PO is the radius of this circle that is equal to 2 units. Chord BP passes through the center of the circle, therefore chord BP is defined as the diameter of this circle. Then we extended side CD by a straight line until it touches the circle. So we actually don't know where the extended side CD will touch the circle. So we'll assume that it will touch the circle at this point, point X. That is not point P. So actually we created here peripheral angle BCX, that it is equal to 90 degrees, and it is not resting on the diameter of the circle, that is PB. And it is a contradiction, because of the fact that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, that is PB. So in order to avoid the contradiction, we must arrive to the conclusion that point X must merge with point P. Okay? And here peripheral angle BCX, it is actually equal to peripheral angle BCP. In this way, we have here peripheral angle BCP that is equal to 90 degrees, and this peripheral angle that is equal to 90 degrees indeed rests on the diameter of the circle, that is PB. Otherwise, if point X will not merge with point P, we will get the contradiction that we will have a peripheral angle that is equal to 90 degrees and it is not resting on the diameter of the circle. And in order to avoid the contradiction, point X must merge with point P. Okay? That is to say, peripheral angle BCX must equal to peripheral angle BCP, that is equal to 90 degrees, and this peripheral angle that is equal to 90 degrees, it will rest on the diameter of the circle, that is BP. Okay? Here PB is the diameter of the circle, therefore it is absolutely a straight line. PB is a straight line, and we have the rule that the sum of the angles on one side of the straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, the sum of the angles here must be equal to 180 degrees. So which angles we have here? this angle equals to 90 degrees, plus angle AOB, then in total they must be equal to 90 degrees. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles here, at point O on the other side of PB 280 degrees, this angle must be equal to 90 degrees. So angle AOP equals to 90 degrees. Okay, so actually here triangle PDO is a right triangle. We implemented the Pythagoras theorem on the right triangle, triangle PDO. Here PD square equals to OD square plus PO square. In the right triangle PDO, PD square equals to PO square plus OD square. So PD square equals to PO square. PO is 2, so PO square is 2 square, that is 4, plus OD square. OD is 1, so OD square is 1 square, that is 1. So in conclusion, we found out that PD square equals to 1 plus 4, that is 5. We took out of this equation and we found out that PD equals to a square root of 5 units. Here PD equals to a square root of 5 units. Then we focus on the right triangle, triangle DOP. According to the Pythagoras theorem, dB square equals to OD square plus OB square. dB square equals to OD square plus OB square. DO equals to 1, so DO square is 1 square, that is 1. Plus OB square. OB equals to 2, so OB square is 2 square, that is 4. And dB square equals to 1 plus 4, that is 5. We took out of this equation and found out that dB, the hypotenuse dB, also equals to the square root of 5 units. Okay? Then we extended the radius OEO by a straight line until it touches the circle at point Z. Point O is the center of the circle. Point Z is the point of the circle itself. Therefore, OZ is the radius of this circle that is equal to 2 units. Then we implemented rule number 1 in our drawing. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Okay? In our drawing, we have chord AZ that intersects with chord CP at point D, therefore AD times DZ equals to CD times DP. Again, chord AZ intersects with chord CP at point D, therefore AD times DZ equals to CD times DP. According to rule number 1, of course, AD is 1, DZ is 1 plus 2, that is 3, CD is the missing line segment, and DP is square root of 5. So 3 equals to square root of 5 times CD. We divided this equation by square root of 5 and found out that CD equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle, triangle CDB. According to the Pythagoras theorem, dB square equals to CB square plus CD square. dB square equals to CD square plus DC square plus CB square. dB is square root of 5, so dB square is square root of 5 square, that is 5. DC is 3 over square root of 5, so DC square is 9 over 5. Plus CB square, that is the missing line segment. So we found out that 5 equals to 9 fifths plus CB square. We subtracted 9 fifths from this equation and found out that CB square equals to 5 minus 9 fifths. We multiplied 5 by 5 and then we divided it by 5 in order to have a common factor with this expression. 5 times 5 is 25, so 25 minus 9 is 16. So we have 16 over 5, that is equal to CB square. We took out of this equation and found out that CB equals to 4 over square root of 5 units. Here, now the area of this blue white triangle will be equal to the base of the triangle, that is DC, times the I to the base, that is CB over 2. The base DC times the I to the base, that is CB over 2. DC is 3 over square root of 5 units. CB is 4 over square root of 5 units, all divided by 2. 3 times 4 is 12. We have 12 in the numerator, and square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6. So in the numerator we have 6, and in the denominator what is left is only 5. So the area of the blue white triangle equals to either 6 over 5 square units, so in terms of numbers it is 1.2 square units. We finished with the first method. Then I presented to you how to find out the area of the right blue triangle according to the second method. In the second method, we use all the things that we already found out in the first method. This angle equals to 90 degrees according to the first method. AD equals to 1, DO equals to 1, and then we completed the quarter circle to a semicircle. We already found out in the first method that dB equals to square root of 5 units. And here we extended side BO by straight line until it touches the circle at point P. Point O is the center of the semicircle, point P is the point of the semicircle itself, therefore PO is the radius of the semicircle that is equal to 2 units. Okay? Then we extended side CD by a straight line until it touches the circle, and in method 1 we proved that when we extend side CD by a straight line, it must start the circle at point P and only at point P. Okay? According to the first method, dP equals to square root of 5 units and dB also equals to square root of 5 units. And then this angle equals to 90 degrees according to the first method. We define this angle as theta, therefore this angle must be equal to 90 degrees minus theta. The same thing is true in the right triangle PCB. This angle is theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the triangle to 180 degrees. This angle must be equal to 90 degrees minus theta. Then we prove that this right triangle PDO is similar to the right big triangle PCB. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are equal both to 90 degrees, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And we have a common angle that belongs to both triangles, therefore this angle equals to itself. We actually proved that all three angles of triangle PCB can work to all three angles of triangle PDO. Therefore, triangle triangle PDO is similar to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that PD over PB equals to DP over CB equals to PO over PC. PD is equal to 5 units, PB is 4, DO is 1, and CB is the missing line segment, PO is 2, and PC is equal to 5 plus DC. We derive the first equation from this bigger equation, that square root of 5 over 4 equals to 1 over CB. We cross multiply this equation and found out that square root of 5 times CB equals to 4. We divided this equation by square root of 5 and found out that CB equals to 4 over square root of 5 units. Here CB equals to 4 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle, triangle CDB. Here dB square equals to DC square plus BC square. dB square equals to DC square plus CB square. dB is square root of 5, so dB square is square root of 5 square, that is 5, plus DC square, that is missing line segment, plus CB. CB is 3 over square root of 5, so CB square is CB is 4 over square root of 5, so CB square is 16 over 5. We subtracted 16 fifths from this equation and found out that 5 minus 16 fifths equals to DC square. We multiplied 5 by 5 and then we divided by 5 in order to overcome a factor in this expression. 25 minus 16 is 9, and so we have here 9 over 5 that is equal to DC square. We took out of this equation and we found out that this is equal to the square root of 9, that is 3 over square root of 5. So in conclusion, we found out that DC equals to 3 over square root of 5. Now it is very easy to find out the area of this blue right triangle. The area will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Here, this is the base times the height, that is CB over 2. This is 3 over square root of 5. CB is 4 over square root of 5, all divided by 2. 3 times 4 is 12, so in the numerator we have 12. Square root of 5 times square root, in the denominator we have square root of 5 times square root of 5, that is 5, times 2. 12 over 2 is 6, so in the numerator we have 6. In the denominator what is left is only 5. So in conclusion, we found out that the area of the blue right triangle BDCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. So in both methods we arrive to the same result, that the area of the blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, thank you very much.